We have a marine debris problem. One of the difficulties with solving it is that we don't really know how much there is or what the distribution looks like. Accurate estimates would be useful in tracking the effectiveness of waste management practices as well as raising awareness for the scale of the problem. One of the current methods for quantifying the amount of marine debris is through remote sensing. Remote sensing methods can reach remote places and scour large areas. They are frequently complemented by deep learning algorithms which can detect and classify different categories of objects. In my research, I used an algorithm called You Only Look Once, or YOLO v5, to build a marine debris image classifier. I improved an existing 7-category classifier to a 9-category classifier that can detect plastic bottles, plastic buckets, plastic bags, fishing nets, plastic straws, food wrappings, fish, aluminum cans, and cigarette butts, all of which comprise the most common debris items found at the shorelines and the seas. The bulk of my work involved the investigation of 2 possible methods that could augment deep learning algorithms by providing counts for different categories of marine debris, resulting in a fully automated quantification process. The first method is called region of interest line counting. A line with a certain width is placed at the center of the screen to track when the center of an object's bounding box, also known as its centroid, resides in the line at some point, and its label is used to increase the count of the appropriate category. The second method is called centroid tracking. The tracking works by assuming that for a given object, the distance between its 2 centroids in 2 consecutive frames is smaller than distances to all other centroids. Assigning unique IDs for each bounding box present in a frame allows for tracking across the entire video. Additionally, I tracked the number of frames that an object was on screen. The image classifier might label the same object differently between frames, which would cause overcounting because the same object has multiple IDs. So setting a threshold for the number of frames that an object needed to be on screen before it was counted would increase the probability that the count for the category more frequently associated with the object would be correctly incremented. I also tracked the number of consecutive frames that an object did not appear on screen. If an object leaves the frame and sometime later an object of the same category appears where the former object left the frame, we need to be able to ensure that these 2 are treated as separate objects. Once an object disappears from the screen for a certain number of frames, we no longer track the object. I tested both methods using a retrained version of the 7-category classifier and on a video containing objects from all 7 categories. Both methods had the same peak accuracy of 72%, where accuracy is the number of correctly counted objects in relation to the actual counts. However, it is important to note that nets tended to be overcounted in the ROI method because they occupied the entirety of the frame, and the net centroid would linger within the ROI line for multiple frames, so disregarding this effect led to the 72% accuracy value for the ROI line method. The ROI method's performance depended heavily on how a video was shot, in particular how fast the camera panned over objects, while the architecture of the centroid tracking method only requires an object to remain on screen for some time for it to be counted. After testing on more videos, centroid tracking was deemed more reliable and selected for further testing. For the final version of the classifier, I collected images of aluminum cans and cigarette butts to train a 9-category classifier and tested it on a collated video containing 43 items in total from all categories except fish. Here, the centroid tracking method had an overall accuracy of 79%. Though further testing is needed to determine the algorithm's robustness, the YOLO v5 classifier and centroid tracking technique could be a viable option for estimating the abundance of marine debris on shorelines and at sea. Its greatest potential can be realized through the contributions of citizen scientists through training data collection or filmed video footage to test the algorithm on. These contributions would help improve the accuracy of a fully automated marine debris quantification process. Deploying deep learning to estimate the abundance of marine debris from video footage, in turn, would allow us to accurately monitor waste management practices.